Yeah, good morning, everyone, and a very warm welcome to the third broadcast episode of Lab Chats. And today we have Christina Dickmeis as a guest again, who you already know from our very first episode. And yeah, today she will tell us how her project evolved and which new technologies she implemented.
Yeah, thank you very much for the introduction. So today I would like to talk about my recent results that I obtained for the improvement of my process in Pichia pastoris. And with this, I also would like to introduce our multiparameter sensors and the dissolved oxygen DO sensor pills for shake flasks. And by this, I would like also to show you how I was able to remove further black boxes in my process for improved bioprocess development. So first of all, I would like to start with a short introduction of the topic and my project. So I'm an R&D scientist in the chemosensor department, and we are working on the development for future shake flask sensors. And my current project is to create enzymes for new sensors. And the tasks that I'm currently working on are, so I choose which enzymes I want to work with and what we need. Then I decide if we need any modifications for this protein for our purposes. Then I check for a suitable expression host like E. coli or Pichia pastoris. I test the very first expression and if the purification is suitable. So check a very rough strategy for this. Then I test if the modifications I did and the expressed enzyme is functional, and I also quickly check how is the stability, if this is suitable for our process, or if the protein is degraded too fast. So for the first few candidates that we have in pipeline, I already did all these steps, and I'm currently focusing in this talk about how I'm now optimizing the production to get enough enzyme for further developments. And what we ultimately want to do is to produce glucose measurements in shake flasks. So I'm working on sensors for this kind of measurement. And to understand why I did the developments and the steps I did, I'm going to present today is I want to know how we started. So when I started in the lab, we just started with the whole team, very new, and the lab was still under construction. And we had a rather old bioreactor that was disassembled and assembled quite a few times, and it was only partially functional anymore. So we needed a new bioreactor with a very long delivery time. So I needed to wait. So I was forced to do the first steps in shake flasks, and we had a fully equipped application lab that was up and running with several shakers, and I could use the cell growth quantifier that we have in-house and the liquid injection system. And by this, I was able to measure online the biomass and also have an automated feeding. So these were the stages when I started first. And at the end now, we have the chemosensor lab fully functional, up and running. We have the new bioreactor available. So I was able to do the first experiments here as well. And I still have the application lab that I'm using quite frequently with several shakers. And we now have the multiparameter sensor available. And I was able to use the dissolved oxygen sensor pills in combination also with the liquid injection system. So by this, I still have biomass measurements from the bottom. I still have the automated feeding system. And we can also measure now fluorescence online and the dissolved oxygen of the process. So before I go into detail of the scientific developments I did, I would like to introduce the multiparameter sensor. So the sensor is still underneath the shake flask, and we measure the dissolved oxygen now with a new module. So we have a readout on the size for currently dissolved oxygen, and also already implemented for pH measurement for future developments. Then we still have an optical readout that's positioned in the middle, and there we can measure the backscatter like we did with the CGQ. And we can also measure certain spectra for fluorescence. So we have a set of available excitation wavelength that we can use and detection spectra. This we currently are using for direct fluorescent measurements, and also is planned to use it as marker detection for later applications when we want to use several pills in the shake flask. We also still have ambient sensors in the system, so we measure the temperature, the shaking speed, the humidity and pressure online as well. And here we have the USB-C port where we use for the connection to the system, for charging, and also for the connection to external interfaces. So our DO sensor pills that can be added to the system now to measure the dissolved oxygen in the liquid can be just throw into the shake flask, and the pill has roughly a volume of 1 milliliter. The pill is homogeneously coated with the chemosensor system that responds to the dissolved oxygen in the liquid. And the caps will be marked with a UV marker for identification that will be read out in the middle of the sensor. And on the side, we have an LED for excitation of the dye and the photodiode for the measurement. So whenever the pill passes by the sensor during shaking, we can create a readout of the oxygen by measuring the fluorescence here. The pill is designed for optimized stable movement under the shaking conditions. And so you get an idea how this looks. You can see the setup. So here you can see the pill floating around the liquid during shaking. And the pill is nicely following the liquid whenever shaking is performed in phase. So here you can also see the full setup with the liquid injection system and the measurement of the red marker here. So now we come to the scientific side. So the production optimization of glucose oxidase and Pichia pastoris that I performed. So I started with Pichia pink strain 1 from Envitrogen. That's the expression system I used, and the glucose oxidase that I use is currently integrated, stable into the genome. And when I work with shake flask, I use 25 milliliters of standard Pichia expression medium. I use 250 or 500 milliliter shake flask, and I always use 24 degrees Celsius as expression temperature. The shaking is performed at 250 RPM with a 25 millimeter throw. And when I started using the bioreactor, I went up to 1.5 liter of medium in a 2 liter vessel. I did a glycerol fat batch with 40 milliliters of 50% glycerol and 200 milliliters of methanol for the later induction. And also here I used 24 degrees Celsius. I used one volume, a vessel volume per minute of aeration and 1000 RPMs during speed. So when I optimized my system now with the first setup that I had, so with the CGQ and the LIS, I was able by step-by-step experiment runs to increase the yields of my product from 3.1 microgram per milliliter to up to 34 microgram per milliliter. So I was able to reach a 10-fold increase over the time. And this was performed in 26 single experiment runs where I always did several shake flask experiments in parallel. So this transfers to over 200 LIS cartridges that I used. So these 26 experiments then can be transferred to 200 single shake flask experiment runs. And this all was done in around 3/4 of a year. So this whole development took nearly 1 year until I had all these results. And during the talk, I would now like to show you why I'm confident that for the next clones that I have in pipeline, I can reduce all these steps to a few experiment runs with the new system, with the MPS and the DO sensor. And I'm sure I can use less than 20 cartridges and 1 to 2 weeks to get similar results for this for these kind of clones. So, and why I am this confident, I would like to show you now. So when I started with the expression, of course, I looked up all the literature, how should a normal expression in PTIA or a good expression in PTIA look like. And of course, the state of the art is to use the bioreactor. So usually we perform a batch phase on 1% glycerol. And when I performed these experiments later in bioreactors, I always use the BioR for biomass measurement online as well. I always measure DO, the dissolved oxygen, and the pH during the whole process. The antifoam addition is triggered if needed. And then I would perform a fed batch phase and a starvation phase. So first, the biomass is increased by a feed of glycerol. And during this time, a pH maintenance is usually triggered because pH tends to fall rather low during this time. And at the end, you perform a starvation phase to make sure that all the glycerol is used up before you switch to a methanol induction phase, where the protein induction is performed via a methanol inducible promoter. So you give first an adaptation shot to allow the cells to adapt to the new C source. So you give 1% of methanol and wait until the dissolved oxygen went up again after the addition of methanol, because then you are sure that all the methanol that you have given to the cells is consumed. And then you start with a constant methanol feed that the cells then can produce the protein and also use the methanol for further growth. And also during this time, usually pH maintenance is triggered in the bioreactor. So when I started, I didn't have the bioreactor yet, so I was forced to start in shake flask, and a normal shake flask run that you find in literature is performed also on in the batch phase on 1% glycerol. Usually you can only measure offline for example, the OD. And the fed batch phase is usually skipped. Usually you increase the biomass by harvesting the cells, centrifugation, and then dissolving the cells in less medium for the induction phase. And then you do a methanol induction phase by giving 1 shot of methanol every 24 hours manually. So I was able to use the CGQ and list system. So I was able to measure the biomass online directly at the beginning of the start of the production optimization. And I also started with 1% glycerol. I was able to see when my cells are finished in their growth and then trigger the feed of methanol. I skipped the fed batch phase at the beginning and directly started with the methanol induction. So I gave 1 adaptation shot, for example, like we did in the bioreactor runs, and then start a constant methanol feed. And by using this system, I was able to test different conditions for the production. So I tested different feeding strategies. So how is the expression when I use this 1 shot every 24 hours, like you would normally do it in the in shake flask, or how does it look when I use the feeding strategy like we do in the bioreactor, so with an adaptation shot and then a constant feed, or what happens when I start directly with a constant feed, for example. And of course, I found out that when we mimic the production like we do it in the bioreactor, I obtained the best results for protein production. I also looked for an optimal time point for induction. I optimized the amount of methanol that we use in the feed, so how much can be consumed by the cells and when do I overfeed the cells. I tested buffering of my feed because I found out that the biggest problem in my shake flask process is actually the lacking pH control. And I also tested out different filling volumes for production. And I checked out the adaptation time. And this is also one of the most, not necessarily surprising, but remarkable results I obtained, in my opinion. So when I checked for different adaptation time, which can vary for each clone in PTIA pasteuris that you produce, between 7 to 12 hours, what you usually find in literature. So you need to check this for every clone that you produce and see how long they take until they adapt to the methanol metabolism. And when I did that for my clone that I'm currently showing you all the results with, I didn't see any difference if I went down to 7 hours of adaptation time. So no real significant difference could be seen for the production of my enzyme. So I concluded, okay, 7 hours should be sufficient. I didn't dare to go lower because it's not reported in literature to find this. And when I was able to do the first runs in the bioreactor, which was roughly at the time when I had these results, I could see that for this clone, exactly after 7 hours, also in the bioreactor, I could see that all the methanol was consumed and that the adaptation time that I've seen here is actually quite well chosen. So the DO recovery in the bioreactor after 1% methanol addition was exactly after 7 hours, and I could confirm these results in the shake flasks here. So the step-by-step optimization that I performed with the CGQ and list system led to the current setup that I'm using. So I always use 500 milliliter shake flask with only 5% filling volume. I use 24 degrees Celsius of expression temperature, 250 RPM shaking frequency with a 25 millimeter flow. I use 4 milliliter of 40% methanol or 8 milliliter of 20% methanol in a buffered system at pH 6. I control the feed with the list with our DOT software, and I do a so-called biomass-based feeding. So the feeding is triggered when the growth rate falls below 0.002 per hour after 30 hours of wait time. I do a 7 hours of adaptation time. So after the first shot is given, I let the system wait for 7 hours, and then a constant feed of methanol is started for 65 hours. And the results are obtained are now in the range of 35 microgram per milliliter with this setup. And now I would like to show you why I'm confident that I can reduce all these single steps now to a very few rounds of experiments, and how I could reduce the amount of trial and error that I had to perform in shake flask with the DO sensors and the multiparameter sensor that we have available now. So the first thing I did when I was able to test the first prototype, I used the expression setup that I showed you before and just used the DO sensor pill and wanted to see how is the dissolved oxygen behaving during my process. And the very first time I was able to see this data, I was actually very thrilled because it's really nice to see this detailed amount of data for shake flasks. And what I could see is here, you see the biomass like it was in all my experiments before. And then you can see the dissolved oxygen. It goes down during the batch phase. It stays down for quite a long time in shake flask until it went up again when the glycerol is consumed. And then you can see that the feed is actually triggered as soon as the dissolved oxygen is up again as well. So the time point that I optimized here by hand was actually quite nice. Then you can see when the methanol shot is triggered, the dissolved oxygen goes down again. And in the 250 milliliter shake flask that you can see here, the constant feed actually started before the dissolved oxygen was up again. But after the first 2 shots, you can see that after each methanol shot that is given by the LIS system, the dissolved oxygen was able to recover. Then the next shot is given. So this nicely hints towards that all the methanol that I use is consumed until the end of my process. So I don't do any overfeeding and we don't have any accumulation of methanol, and the cells are able to use up all the methanol. So you can see all the step-by-step optimizations that I did blindly led to a very nice optimized process. And also I found it very nice in the data that you can see here this little shift during the metabolism adaptation here that we can also see in the bioreactor. So also here you can see this little dot where the metabolism actually then changes until the methanol can be consumed. So you can nicely see this in the shake flasks as well. So the next step I was then able to do is to test out a so-called DO-based feeding. So we implemented a PID controller in the feeding system, so we can control the feed. We can set a maximal flow rate and can say trigger the feed when a certain value of dissolved oxygen is reached, or stop the feed if the dissolved oxygen falls below a certain value. And here you can see just a very rough test when we tested the behavior of the system and try to find out the optimal conditions for our PCR cells. So you can see the dissolved oxygen rate, and we set a trigger point of something around 30–40% of dissolved oxygen. And as soon as the dissolved oxygen goes up, a flow rate is calculated by the system. And then a shot of feeding is triggered. And as soon as the dissolved oxygen goes down again, the feed is stopped. And when the dissolved oxygen does not go down, like we simulated here, the feed continues at the set maximal flow rate. And I did this for our PCR cells. So I used the DO of 30%. So the feed should stop as soon as the DO falls below 30%, and will start again if it falls, if the value is reached again. The remaining conditions stayed the same. So I used the same amount of medium, shaking, and expression temperature. And when I've seen these results, I was rather surprised that because they looked very, very similar to the optimized feeding steps that I did before. So these data are still rather, it's the raw data that I show you. So it's not smoothed out yet, but you can see very nicely during the batch phase, the dissolved oxygen goes down and feeding is triggered in accordance to the biomass signal, like I've did that before. And then you see the DO recovers, and then the PID controller is started, and then we'll start the feed, give a shot of methanol. The feed is immediately shut down because the cells are responding very fast, and as soon as methanol reaches the liquid, the cells start to consume it, and the dissolved oxygen goes down again. And then you can see a very similar feeding profile like we've seen in the optimized process that I showed you before. And when I looked here, you can also see DO recovered each time before the next methanol shot was given. And I found very surprising to find that the same levels of methanol were fed by the system, like I did by all these step-by-step optimizations. And also the expression levels that I observed. So here you can see the data I showed you before with the CGQ and list feeding. And here you can see the DO-based feeding reached the same levels of expression like the step-by-step optimization that I performed. That I did before. And so I was very confident that when I have new clones in pipeline and I directly go for the DO-based feeding, I can tremendously reduce the amount of work I have to perform. So the new expression clones I have in pipeline, I will always use this kind of expression guideline. So I will start the batch phase currently, like I've done it before, on 1% methanol. I use the MPS for biomass measurement and also the DO pills for dissolved oxygen measurement. I'm currently working also on a fed batch phase and starvation phase, where then I would just start with the list with the glycerol feed and then later switch the list drive with the methanol feed. Here currently the biggest challenge is actually the pH maintenance, because during this feeding phase pH is dropping too low, and this prevents the protein production. For the methanol induction, I would also always start with an adaptation shot, because the cells just need the time to adapt the metabolism. But I would do this also with the DO controlled system, so I don't have to each time determine the adaptation time for the clones, but I can use just the dissolved oxygen signal. As soon as the dissolved oxygen is back up, I can start with the constant feed, and this can all be controlled by the system. And then I would control the system by the DO signal, so use the PID controller to make a feedback controlled feeding. And so I don't have to calculate the amount of methanol I need to feed during the time. I don't have to determine the step sizes, and just can use can use the feed as my cells are able to consume the methanol. Yeah, and by this, I actually would like to summarize all the data that I just presented. So I was able to improve the amount of protein that I produce nearly tenfold in the shake flask experiment. And I did this by using 200 single experiments over the course of 1 year. And the benchmark in my bioreactor is currently around 120 microgram per milliliter. And so far I was able to perform 4 single experiment runs, and each run takes 1 week. So, and I only have 1 bioreactor available. So I will rely on shake flask for some more time. And but I'm confident that with the new system, so with the MPS and the DO sensor pill, I'm able to do all these improvements in a few experiments in parallel in 1 week for future developments now. And I hope by all these steps I performed during my process optimization, I could show you how we are working on the optimization of shake flask to better compare our results to the bioreactor. So currently, of course, state of the art is the bioreactor, because we are able to measure a lot during the process. We can measure the biomass, we can perform automated feeds, we measure the DO and pH, and we can parallelize the bioreactor with a high investment. We can measure fluorescent and glucose with high investments. But a lot of people are still relying or need to rely on the shake flask because they don't have all these options available or don't have the investment. And I was forced to use shake flask in the beginning, and I think a lot of people are still heavily relying on these systems. So with the CGQ and LIST system, we are able to already do a lot of improvements, as you've seen. So we can measure the biomass and can automate our feed according to the biomass. And we can still easily parallelize the experiments. And with our new system, we can further provide new data. We can also measure the dissolved oxygen. We can also control the feed in accordance to the dissolved oxygen level. We can also measure the fluorescence, and we are currently working also on a pH measurement and also glucose measurement in the future. So by this, I presented all my data for the PCR process, but because I already mentioned also a fluorescent measurement with the MPS, I also would like to share some of these data with you. So with the MPS sensor below, we can also measure online the production of fluorescent proteins, for example. Here I can show you some data of a simple eGFP expression in E. coli in a standard expression vector in E. coli. And this was performed with an IPTG induction. And you can see the data of a non-induced clone and an induced clone. And you can nicely see the production of eGFP over time. And also we have produced a photo switch protein. So this is DS-RED 1E5. It's also called P-timer vector. And this photo switch changes its fluorescence from green to red. So when it's expressed, you can see a green expression after IPTG and induction. And after some time, the protein switches its fluorescence from green to red. And here you can see over time the accumulation of the red fluorescent. And here, so this later transfers to the total protein amount. And by the green fluorescent you can also translate to the promoter activity during the time. And here we were able to measure 2 different wavelengths online in one with one simple measurement. And last but not least, I would also like to show some impressions from further in-house tests that we performed. So we also just used the system to measure the growth of E. coli with different filling volumes. So we used a 250 milliliter shake flask, E. coli at 37 degrees, and just used 5, 10, and 20% filling volumes. And you can see how much longer the cells need if you increase the filling volumes to consume the medium, and also the growth just takes much more longer, and that's because of course the oxygen transfer changes if you increase the filling volume. And also we can monitor carbon source switches during the production. So here we used E. coli growing on LB medium, which you can see in purple, and E. coli growing in LB medium with the addition of glycerol. And you can see the differences in dissolved oxygen consumption. And so we can also nicely see deoxic shifts in the DO data. And further, we also observed the dissolved oxygen development if you use different shaking speeds. So here you can see in purple an E. coli culture grown at 250 RPM in comparison to 250 RPM. And yeah, you can also see that faster shaking speeds increase the oxygen transfer as long as the liquid stays in phase, of course. Yeah, and by this, I would like to thank you very much for your attention. And I especially would like to thank all the SBI crew who is behind all this system. So yeah, there was a lot of work and effort by all the departments in the development of the new systems. And yeah, I really like all the spirit that we have in the company, and all the nice results we were able to achieve. Yeah, thank you very much.
Yeah, thank you, Christina, first of all, for this great presentation. It's really cool to see what you can do in shake flasks already, and congratulations on your really nice results.